Let's discuss directory implementation. Directories are essential for efficiently storing and retrieving file information in operating systems. It helps in managing how files are organized and accessed on a storage device. Here are the two key methods: linear list and hash table. Linear lists offer simplicity with sequential organization, but may suffer from slower search times. Hash tables provide direct access using hash functions, enabling faster lookup operations. Let us explore the linear list directory implementation. The linear list is the simplest form of directory implementation. It stores file names with their attributes sequentially. It's easy to implement and maintain, making it suitable for directories with only a few entries. However, it has a linear search time complexity, denoted as O of n. Let's explore the operations of a linear list directory implementation, focusing on search and insert operations. The first code snippet shows how to search for a file by iterating through the directory entries and comparing file names. If the file is found, its details are returned. Otherwise, it returns null, indicating the file isn't found. The second code shows how to insert a new file. First, it checks if the file already exists to avoid duplicates. If the file is unique, it's added to the end of the directory. The function returns true if the insertion is successful, and false if the file already exists. Now, let's examine the delete operation and limitations of the linear list implementation. The code snippet illustrates how to delete a file from the directory. It searches for the file by name and, upon finding it, removes it from the list using the splice method. This operation has a time complexity of O of n. The time complexity for search is O of n, insert is O of 1 or O of n if checking for duplicates, and delete is O of n. This implementation is inefficient for large directories due to the linear search time. Performance degrades as the directory size increases, and there is no inherent ordering unless manually maintained. Deletion may require shifting elements. It is simple to implement but not scalable and more memory efficient for small directories, suitable for systems with few files or embedded systems with limited resources. Let us learn about the hash table directory implementation. It uses a hash function to map file names to array indices, providing constant time, O of 1, access in the best case. It's more efficient for large directories, but requires collision resolution strategies. This approach trades memory for speed improvement. It is widely used in modern file systems because of its efficiency in handling large directories. The visual content displays the hash table structure, showing how file entries are organized using hash indices. Each row represents a bucket, with file names stored at specific indices determined by the hash function. Let's explore hash functions used in directory implementation. The first one is the division method. The code shows a simple hash function using the division method. It calculates the sum of ASCII values of the characters in the file name and returns the remainder when divided by the table size. In the example for the file name data.txt, the ASCII sum is 808. With a table size of 8, 808 modulus 8 equals 0. Next is the multiplication method. The code shows a hash function using the multiplication method, utilizing a golden ratio constant. The multiplication method tends to distribute keys more uniformly, reducing clustering, and is less affected by patterns in the input data. Let's explore collision resolution strategies used in hash tables. The first strategy is chaining. In chaining, each hash table bucket contains a linked list of all files that hash to the same index. When a collision occurs, the new file is simply added to the linked list at that position. Chaining advantages include simple implementation and effectiveness, even with high load factors. Disadvantages include extra memory for linked list pointers and potential cache performance issues. Next, we have open addressing, also known as linear probing. In open addressing, all elements are stored in the hash table itself. When a collision occurs, we search for the next available slot, according to a probing sequence. Open addressing advantages include better cache performance and no need for extra pointers. Disadvantages include sensitivity to clustering and complex deletion processes. Let's dive into the hash table directory operations. The first is the search operation. The code demonstrates how to search for a file by computing the hash index and checking if the file exists at that index. The best case time complexity is O of 1 for direct access, while the worst case is O of n if all files are in one bucket. On average, with a good hash function, the time complexity is O of 1. The second operation is the insert operation. The code shows how to insert a file into the hash table by calculating the hash index and adding the file to the appropriate bucket. Advantages include fast access for large directories, efficient frequent lookups, and good scalability with directory size. Let's compare linear lists and hash tables. For search time, linear list has a poor performance of O of n, while hash table has a good performance of O of 1 on average. For insert time, linear list has a moderate performance of O of 1 for end insertion, while hash table has a good performance of O of 1 with a good hash function. For delete time, linear list has a poor performance of O of n for finding and removing, while hash table has a moderate performance of O of 1 with chaining. Memory usage is low for linear list and higher for hash table because of table and overhead. Linear list implementation is simple, while hash table is more complex. Scalability is poor for linear lists when there are large directories and excellent for hash tables. Linear lists can maintain order, while hash table has no inherent ordering. In conclusion, use linear lists for small directories, embedded systems when memory is limited, or when maintaining order is important. Use hash tables for large directories, systems requiring frequent lookups, modern file systems where performance is critical. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.